This is part 3 on our discussion about the strengths of acids and bases. In this video, we're going to calculate the pH of strong and weak acids and bases. Let's start with this one. HCl is a strong acid, thus they are 100% ionized. What is the pH of 0.0010 molar of HCl? So here, we're asked to determine the pH of this given amount of HCl. Again, pH is equal to the negative log of the concentration of hydrogen ions. So before we can solve for the pH, we need to determine the H plus concentration first, and we can do that one by doing an icebox. That is initial, change, and then equilibrium. So for the initial concentration of HCl, it's given here, it's equal to 0.0010 molar. Then of course the products at the initial or before the reaction, they are not formed yet, so that's 0 for now. Then with the change in the concentration, again HCl is a strong acid, therefore it will completely react to form H plus and then Cl minus. So meaning all of this 0.0010 will be used or will be consumed to form the product. So this will be completely used, that is minus 0.0010 molar. And then if we look on the coefficients in the balanced chemical equation, there is a 1 to 1 to 1 ratio. So meaning if we lost this amount in our HCl, the same amount will be formed for H plus. That's also 0.0010. The same thing for Cl, that's equal to 0.0010. Again, that's based on the ratio on the balanced chemical equation. 1 to 1 to 1 means whatever is lost from this one is gained by the same amount on the products. And since this one are the products, we put here plus because again they are increasing in concentration over time. And then for the equilibrium concentration, simply add the initial and then the change in the concentration. That's positive 0.0010 plus negative 0.0010 is obviously equal to 0. Then 0 plus this number is equal to 0.0010. The same thing, 0.0010. Right now we have the equilibrium concentration of H plus, and we can now solve for the pH of this one. The pH is again the negative log of the concentration of our H plus ions. And then we have here our H plus concentration. This one is equal to 0.0010. And then for this one, we need to use our calculator. That's equal to, again, sorry, 0. What's happening? 0.0010. 0.0010, get the log of this, the negative log, so meaning the negative log or the negative of negative 3, that's equal to positive 3. So the pH for this one is 3, and that is expected because this one again is an acid. Again, acids, their pH is less than 7. Let's go to another one. This time it's a strong base. A strong base, the same with a strong acid. They are completely or 100% ionized. We're asked to determine the pH of this given amount of our base. So of course, the pH is equal to the negative log, again, the negative log of the concentration of our H plus concentration. But this one is a base, and here we can only calculate for the OH minus concentration. So for this one, actually, we need to get first our POH, because from the POH, of course, is equal to the negative log of our concentration of our hydroxide. So our first step is to get the concentration of OH minus and then determine our POH. And from our POH, we can use this equation, pH plus POH. It's equal to 14, right? And if we know our POH, then we can determine our pH later. So again, our first step is to determine the OH minus concentration. And with that, let's do an icebox. That is initial, change, and then equilibrium. So for the initial concentration of magnesium hydroxide, it's given here, that's equal to 0.0010 molar. And then for our products at the initial, again, that's always 0. We don't have any of them. And then for the change in the concentration, this one is a strong base. The same thing, it's completely ionized. So this uh, all of this amount of our given base will completely react. And then if we look on the balanced chemical equation, there's a 1-to-1 ratio between magnesium hydroxide and the magnesium ions here. So the same number, if we have 0.0010, the same thing for this one, 0.0010. And then that's plus because again these are the products and products are increasing over time. And then for our OH minus here, it's different, right? There's a 1-to-2 ratio here. So that's times 2 sa magnesium. So if we have 0.0010 here, again, double of that ang change on our OH concentration. That would be 0.0020. Again, that's double because it's based on the coefficients in the balanced chemical equation. This tells us the ratio between their change in concentration. That's also plus because this one is again a product and product are increasing over time. Then we'll get the sum of this one. Add that's obviously equal to 0. Add this one is equal to 0.0010. Then for this one 0.0020. What we want here is our OH minus concentration, so we'll focus on this one. And from our OH minus concentration, we can use our POH. So let's find out the POH of this one is equal to, again, the negative log of the concentration of our OH minus, which is equal to 0.0020. Okay, then let's find the log of this one. 0. Again 0.0020, 0.0020. Let's get the log of this. The negative log would be 2.7. Let's make this 2.7. So the POH for this one is 2.7. Again, we're asked for the pH of this one. So we can use this equation, pH plus POH. pH plus POH is equal to 14. So our POH is equal to 2.7. To find out for the pH, subtract lang. So pH is equal to 14 minus 2.7. That's equal to, no loss, 14 minus 2.7 is equal to 11.3. So the pH for this one is 11.3, and this one is expected because again this one is a base, so the pH of bases are above 7. Let's go to another one. This time this one is a weak base. Therefore a weak base, they are not 100% ionized. We're asked to determine the pH of this one. Again, for the pH is equal to the negative log of the concentration of H plus ions. So we need first to determine the concentration of H plus in this one. So we need to do an icebox, initial, change, and then equilibrium. At the initial, we have 1 molar of our reactant, acetic acid, then 0 of our products. And then for the change in concentration, again, this one is not 100% ionized. So, so uh, it's impossible to know the change in concentration here. For now, let's put here some X. Then, of course, it's minus because it's the reactants. And then if you look on the balanced chemical equation, there is a 1-to-1-to-1 correspondence, so meaning the same value for this one. Then again here we have plus and then plus. Again, this is 1x, 1x, 1x. That's based on the balanced chemical equation. Then here we have the equilibrium concentration, the sum of the initial and then the change. That's 1 molar minus x. Then here we have x, and then here we have an x. Our Ka here is very, very small. Again, when K is much, much lesser than 1, this reaction favors the reactants. So meaning there will be less change in the concentration of our reactants here. So we expect that this X here will be very, very small. So here we are going to make an assumption X will be approximately 0. So if we assume this one is 0, then 1 minus 0 is equal to 1. So here we have 1 molar for this one. then here we have again x, and then here we have x again. So next we are again finding for the concentration of H plus, but for now it's still x. So we need to find out the value of x on this case. So what should we do? We can use our equilibrium expression. Again, our equilibrium expression for this one is always equal to the concentration of our products H plus raised to the power of 1, because again that's 1 in the coefficient. Since it's 1, we don't need to write 1 here. Then multiply to the other products, we have the acetate C2H3O2 minus over the concentration of our reactants. We have acetic acid HC2H3O2. Again, this one is an acid, so we put here Ka, and for the Ka for this one, it's given in the problem. That's 1.8. 1.8 times 10 to the power of negative 5. Then for the concentration of H plus, we have X for now. Then for the acetate, it's also X for now. And then for the concentration of acetic acid, it's 1 molar. So 1 molar. And then we need to find for X. X times X, that's X squared obviously. And then 1 molar, 1.8 times 10 to the power of negative 5. Let's cross multiply. That's obviously 1's almost. Then 1 times x squared, obviously x squared. Then we have 1.8 times 10 to the power of negative 5. Negative 5 times 1, obviously 1.8 times 10 to the power of negative 5. And then to find for x, find the square root of both sides. That is x is equal to, again, 1.8. 1.8 times 10 to the power of negative 5. Let's get the square root of this is equal to 0.0042. Let's make this 0.0042. 0.0042. So x is equal to 0.0042, and again, this is the value of our H plus concentration. Eraser. Again, here x is equal to 0.0042. The same thing for this one, 0.0042. And again, we are finding for the pH. So we need to look for the concentration of H plus. And again, that's here H plus is equal to 0.0042. So we can now solve for our pH. Again, the pH is equal to the negative log of the concentration of H plus ions. Negative log, then our H plus here is equal to 0.0042. Then what's the answer here? 0.0042. We get the log of this. The negative log for this will be 2.38 or 2.4 na lang. Okay, let's make this one 2.4. 2.4. So the pH for this one is 2.4. And this one is expected because again this one is, okay, it should be an acid by the way. So it's an acid obviously. So this one is an acid, therefore the pH must be less than 7. And this one is correct. Let's go to the next one. We have ammonia. Ammonia is a weak base, thus they are not 100% ionized. Let's determine the pH of 0.10 molar of ammonia. So the same thing kanina. So since this is a base, we can only calculate for the OH. Then after the OH, we'll get the POH. Then after the POH, we can calculate now for the pH. So first, we need to determine our OH minus concentration here, and we can do that one by an ice box. Again, this one is liquid, so again, liquids are not included. Okay, they are not included in uh, our equilibrium expression. Ice table, again, this is liquid, not included. So our initial concentration of ammonia is 0.10 molar. Our products are obviously 0. Then for the change here, this one is again a weak base, so this is not 100% ionized. So here we'll put some X first, another thing here X, and then another X here. Of course, products decreasing, I mean our reactants decreasing, then our products are increasing over time. Then here we have 0.10 minus X. Then here we have X, and then we have another X over here. Our KB is the same thing. It's very, very small. So here we're going to make an assumption. Here X is approximately 0. Approximately 0. So here if X is 0, then it will be 0.10. 0.10. Okay, 0.10 molar. Then for this one we have X. Then we have an X. The same thing to calculate for the OH minus concentration. We need to find out the value of X here. So the same thing, we need to make an equilibrium expression for this reaction. That is K is equal to the concentration of the products, ammonium, NH4 plus, times the concentration of OH minus over the concentration of ammonia, NH3. And again, this one is a base. We put here Kb. Our Kb here is given on the problem. That's 1.8 times 10 to the power of negative 5. Our ammonium here, that's still X for now. So we'll put here X. The same thing for the OH minus concentration. It's also X. Then for our concentration of ammonia, that's 0.10 molar. 0.10. Again, finding for X. X times X, X squared. Copy the other things. 1.8 times 10 to the power of negative 5. Cross multiply. Of course, merong 1 sa abos. 1 times x squared is equal to 1.8 times 10 to the power of negative 5 times 0.10. Calculator. 1.8 times 10 to the power of negative 5 times I'm lost, sorry. 1.8 times 10 to the power of negative 5 times 10 is equal to 0.30 then 18. 0.00018. Am I right? Yes, so to get the x, square both sides. Get the square root of both sides. So the square root of x squared is x. Then the square root of 0.0018. Let's get the square root of this one is equal to 0. Let's make this one 0.13. 0.013. 0.013. And so we have this one. We have our OH minus concentration. Again, the x here, x is equal to 0.013. X is equal to 0.013. The same thing for this one, 0.013. So from our OH concentration, we can now compute for our POH concentration. Negative log of the concentration of our OH minus. Sorry. The next one, we have the negative log. Our OH concentration here is equal to 0.013, 0.013. Then if we solve this one, the negative log of 0.013, let's get the log of this is equal to 1.9. That is 1.9. So the POH here is 1.9. Okay, 1.9. So next, to get our pH, again we're asked for the pH here. The pH, again the pH plus the POH is equal to 14. Our pH is unknown. Our POH is 1.9. 1.9 ang POH. To solve for pH, that's subtract lang 14 minus 1.9. Sorry. Then the pH here is equal to 14 minus 1.9. Where is that? 14 minus 1.9. 14 minus 1.9 is equal to 12.1. So the pH here is equal to 12.1, and again, that's expected because this one is a base.